the map, I'm the map. If there's a place you gotta get, I can get you there, I bet. I'm the map. I'm the map, 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 I'm the map!
Okay. Hi, everybody. Welcome to Orgoland Lecture 25A, which essentially is the last phase, and the beginning, excuse me, of the last phase of our Orgoland semester, where we really transition from looking at SN1, SN2, E1, E2 mechanisms and stereochemistry. You've learned all that now, and now the last phase is truly the poetry of Orgoland. Can you make different functional groups? And we will just start diving in to how to make lots of different functional groups, which is the poetry really of all of organic land. Okay. If you want to be successful in this last phase, this is the part of Orgo that students often think, if I'm going to learn reactions and synthesis and make different functional groups, I have to put everything on a flashcard and memorize it all. I disagree. But I do think you need to travel around Orgoland a lot to get all of those syntheses in your head. And some of them are already there. So one recommendation I'd suggest is to make this functional group roadmap and really grab as big a piece of paper as you can possibly get, huge, to make a big fold-out roadmap of all the roads and all the places you can go see in Orgoland. Like these are the main centers of Orgoland. Alcohol City is right in the middle, and we've already learned how to do some chemistry of taking alkyl halides to alcohols. We've already seen some of that, and how to take alcohols to alkenes. These are possible reactions we could do in functional group transformations. There will be more. So our Orgoland map is going to get bigger. We're going to see nitriles maybe already, and ketones, aldehydes, carboxylic acids that we haven't seen yet. They're coming up. You know, some of these I put up here that you should feel comfortable on how to actually get. But do you have to go through multiple roads, or can you get them directly from alcohols, for example, directly to nitriles, or alcohols directly to alkanes? Can I get there directly? And so that's where we need roads. The one road we know we can use is alkenes. Let us get to alkanes. This was the last one that we learned in the last section, a little jump out that I love to show. Okay? But in all honesty, there are tons of roads everywhere and reactions everywhere, and some of them we've seen, like the alkyl halides to acetates, which is a form of specific kind of ester. We've seen how to do that nucleophilic substitution, but we were so wrapped up in the nucleophilic substitution process, we might have forgotten that we're actually doing a functional group transformation. So notice all these roads. And some of these roads actually go both ways. I can take an alcohol and I can turn it into an alkene. We know how to do that with E1 and E2. But do you know how to take an alkene and take it back to an alcohol if you want? We're going to see how to do that coming up. So please start drawing your roadmap with the reactions over and around the arrows that you see, and make it as big as possible because the map is going to grow. We're going to learn to make more functional groups like halohydrins and epoxides and amines and alkynes. So the map is just going to get bigger and bigger. And to give you a sense of how big it might be when you get done with it, I thought I'd show you one student's representation of her Orgoland map. This is what a student of mine did several semesters ago. When she was studying for her final exam, she translated everything that she knew onto a whiteboard in our science center. And it pretty much scared all the other biology students away, all that Orgo on one big board, but it allowed her to coalesce everything that she was trying to learn for this remaining part of the semester and put it on one space and give her an overall view of what is Orgoland all about. And sometimes it's this overall picture that's easier for us to figure out, even though it looks chaotic, because there's certain roads that I can only take from certain functional groups. Okay? If you want to see more of these functional group roadmaps, they're out there everywhere. There's Lec25a does one. And then you can even find more complicated ones. Oh my God, it scares the crap out of me. But I think these are not helpful because somebody else made them. And I think what'll help get these reactions into your head and all the synthesis into your head for the remaining part of the semester is if you generate your very own roadmap. Because then you will travel down all these roads yourself, you will experience them, and it would be just like going to France and Europe or anywhere else. Just traveling, you experience the roads yourself, you remember them yourself. Okay? So go ahead and start this process, and then you can just keep adding to your big roadmap as we go through the rest of the semester. All right? This isn't the only way, but I found this is one of the very helpful ways to learn all of our organic land reactions. Okay? Cool, and then you can save it for later and maybe sell it to somebody. Woohoo, big money. Okay. All right. Let's now look at how we can synthesize alcohols. How do we travel to Alcohol City from anywhere in our roadmap? You have seen some of this before, haven't you? If I asked you to synthesize these alcohols from an alkyl halide of some kind, this should not be new to you. And that's what I also want you to hold on tight to, that even though we're now venturing into chapter 10, they're just reiterating and going back to a lot of the chemistry I've already shown you throughout the semester. So hold on tight to that, okay? Because if you were to synthesize these, I'll give you a second, what would you use? What alkyl halide and reagents would you use to make these two alcohols? Pause. 5, 4, 3, 2, 1. Okay, let's see what I would use. Okay, I want a primary alcohol, which means I need to start with a primary alkyl halide. Okay, so something like 1, 2, 3, 4, 5 carbons, one bromopentane. And since it's so unbulky on a primary, I can add a strong base like OH minus and not have any concern at all that elimination is going to happen. No elimination, just nucleophilic substitution. So this is very glorious and easy, and we've seen this. Hang on tight. You know how to make a primary alcohol. Could I do the same thing for the tertiary alcohol? If I were to try to add OH minus to this starting material, T-butylbromide, the OH minus in this process would be disaster, right? This would do E2. Too bulky to do an SN2 reaction. So an elimination would take place with this little strong base. So let's not do this. Let's follow this synthesis along in a much gentler fashion, using a gentler source of OH. And let this tertiary bromide just fall off in an SN1 fashion. And have this water jump on as soon as the carbocation is formed. And then, and only then, will H plus fall off my water to create a nice neutral tertiary alcohol. So this should be familiar too. How about this one? What if I want to make a secondary alcohol? What could I use? Well, if I start with a secondary, oops, let's see if I can erase that. Oh, almost. Okay, never mind. Let me get the structure right. Down, up, down. If I start with this secondary bromide, okay, if I were to use OH minus, could I just do an SN2 reaction on a secondary carbon? Right. No. No, 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 no. So this is E2 again. Zaitsev's rule would produce the most substituted alkene, not my secondary alcohol. Could I use water to do this reaction in an SN1 fashion? Sort of. This would be a very slow reaction because it's not on a tertiary carbon, which SN1 reactions love. So this would be extremely slow. Not very high yielding of a reaction. And therefore, what I'd like to do is show you a better way. The best way to ever make a secondary alcohol. Okay? So here's the premise. Again, remember, I can't use a strong base because that'll end up making me the alkene product. So what's the solution? How do I avoid this problem? Well, the solution is to use something like something that will turn into an alcohol really easily. So it's a two-step process. Okay? It's very similar to when we took our alcohols and made them into good leaving groups with tosylates and mesylates. We had to do something first to make them better. Same story here. We're going to take our strong base and not use it as our initial nucleophile up above in this synthesis, as you see. We're going to start with a synthesis that uses the acetate. This is a much weaker base, if you remember, due to this resonance structure that is occurring, that can take place here. But this is still a good nucleophile, this acetate. So I can do this and use this acetate as an SN2 reaction on my alkyl halides with no fear of ever doing elimination. So I get one step closer to my alcohol. I change the bromide and I get to add an oxygen. Ooh, I'm almost there. Almost there. It's really cool. Okay? So let's look at the details of how do I transform it completely to a secondary alcohol. Okay? So here are the details. Start with any alkyl halide, essentially any good leaving group on a secondary carbon. And the goal here is to make a secondary alcohol. So as we saw in the last slide, we actually can use this acetate to act as a nucleophile in an SN2 fashion. Notice the DMF, the aprotic solvent, makes it go faster. Great SN2 reaction to produce this acetate, and Br minus falls off. Okay? So now we have this acetate, this ester. Cool, we just learned how to make esters. Woohoo, skip that chapter or section. Okay, we'll come back and maybe revisit it soon. But this is not magic. I know how to do a nucleophilic substitution and add an ester like an acetate as a nucleophile. The question is, how do I get it from this acetate to the secondary alcohol? So here's where the kind of second step cool craziness takes place. If you add any source of OH minus at this point, this OH minus is going to look for the most partially positive site on this entire molecule. Who is the most positive? Because as you remember, Orgoland is all about plus loves minus. So plus loves minus is all I have to worry about. Who's the most plus? Well, notice this carbon here has 3 oxygen bonds to it. 3 oxygen bonds on that carbon. Okay? Oh, my hand just disappeared. Yeah. 3 oxygen bonds on that carbon over there. Sucking electron density away, which makes it very positive. More so than this little carbon over here, which only has one. So what carbon or species does the OH minus fall in love with? It falls in love and wants to react with this carbon. Okay? Now, I could show you the full mechanism for this reaction, but it's a little convoluted, and I'm afraid I'll lose you in the entire process because I want to just show you the Cliff Notes mechanism for this reaction. The Cliff Notes mechanism for this reaction is if I'm forming a bond with that carbon has to lose a bond. And so sooner or later, this bond breaks between the C and the O, okay? And forms these two products. So I end up getting a negatively charged oxygen, an alkoxide, and this acetic acid, the main species in vinegar. But keep in mind, this is now an acid. So immediately, as soon as this mechanism happens and these two fall apart, almost exactly at the same time, this acid will react with that strong base, that alkoxide. This will jump over and grab this H immediately and take that little bond in there and give it to the oxygen. Immediate protonation of the alkoxide. And guess what you just made? Yep, you guessed it. You just made your secondary alcohol. Boom! In tons of ways. Tons of it is made. It's a very efficient synthesis. It's very high yield. And the leaving group here is much weaker of a base than this O minus that you started with here. Okay? Or the O minus that you started with there. So the acetate not only was a good nucleophile at the beginning of your reaction, but once you isolated the acetate, you could then add the second step, add the OH minus, and produce an acetate leaving group that has no problem falling off. Okay? So take-home message. If you want to make your secondary alcohol, please make it a secondary acetate. Okay? And this occurs by an SN2 fashion, so be on the lookout for inversion of stereochemistry at that secondary carbon. But once I make that secondary acetate, it can react with OH minus very quickly and easily to become a secondary alcohol. Problem solved. Cool. Okay, so let's review today's sites in Oregon. I thought I'd throw up some other sites that you might have traveled and have no problem remembering how to get to these maybe, because you've traveled to these sites lots of times. So my hope is just keep practicing, as you'll see in this video and elsewhere. Keep practicing traveling to these Oregon sites like Alcohol City, and it'll be just as familiar to you as traveling to these sites, which I know you all miss, as I do as well. So keeping in mind that some of the sites I show you in Chapter 10, you've already seen before. So hold on tight to those. That should make your life a little easier. All right? Let's practice. I'll give you a chance. Pause, try these problems, and see if you come up with the same answers I do. 5, 4, 3, 2, 1. Ready? Cool. All right. This is what should happen. Again, labeling this is primary allylic. Next to that double bond. Makes it a little different than aliphatic. Does it change its stereochemistry? Does it change the way it might react? No, it's still primary. Don't even worry about the water that's there because I have a strong, strong base. So is it going to go elimination? The only choice you can do is SN2 or E2. This is going to go SN2 because of the primary. Okay, so you're going to generate this final product is hopefully what you guys wrote for the answer. And you just made yourself a primary allylic alcohol. which could then be used in another synthesis in your roadmap to take it to alkenes or somewhere else on the roadmap that we'll play around with in the next few videos. Okay? The one down below. Did you spy and pay attention to the stereochemistry for this one? Notice that bromide is a wedge. So, did you take that wedge and do an SN2 reaction with the acetate and create the inverted stereochemistry of the O, C double bond O, CH3? This methyl helps us keep track of the fact that the chirality changed for that carbon when it did a backside attack. Okay, so now I can add my KOH. It'll attack this carbon here, which is known as the carbonyl carbon. And we will end up with our final secondary alcohol. But notice all the chemistry is happening out at the carbonyl carbon, so the stereochemistry remains the same now at that oxygen of the acetate. All right? I hope you got these two. If not, guess what? We can practice some more and some more. Oh, like with this one. Cool. Slightly different way to phrase this idea. And I'll just keep bringing all sorts of stuff back to keep us up to date on all the cool chemistry, because you do know how to do and make alkenes from these. You do know how to make nucleophilic substitution reactions. So take a second here and see if you can tell me which reaction gives the highest ratio of nucleophilic substitution products, meaning it favors the nucleophilic substitution reaction over the elimination product, that those would be the least favored in one of these four syntheses. Okay? And feel free to draw out the products for these, each one that you think would be the major product for each synthesis, while I look at these pretty flowers over here. Wow. It's almost springtime here. Those are really pretty. Okay. Ready? Well, let's go through each one. Strong base, E2. So please, hopefully you drew the major product was the elimination product. So that's not a good answer. This is the shorthand abbreviation. If you haven't seen it before, I know you have, but it might not just be familiar. This is the abbreviation for when I want you to add CH3, C double bond O, O minus. This is the abbreviation for the acetate. So please learn to spy this, because this was our wonderful SN2 good nucleophile weak base that's going to end up making a large amount of major product. Whoops, C, O, CH3, and no E2. This looks pretty good. Okay. The one on the bottom could do substitution, but it's not a strong base, so it's not doing E2 or SN2. Throw those out. The only thing it could do is a little SN1E1. And the fact that I've told you there's heat present means that E1 is favored over SN1. I figure it's never a bad thing to review this stuff, because it's never going away. We're going to keep playing with it as we build our functional groups. So this product still would make mostly an E1 product, okay, an elimination product. And again, down here, I just wanted to show you, it's not OH minus. Could it be something else? Could I use this to make the ether? No, it's still a strong base. So this one still favors E2. And so notice we have a lot of elimination products written on the board on the slide here. So really the answer to this one is B. That would be the one that would make the most substitution products. Okay? All right. I hope this has helped. And I hope you're safe and well. And I'll see you in lecture 25B coming up soon. Bye.